Okay, I think it's time to get started. Welcome to the second and last session of today. First speaker is Garvesh Raskutti from University of Wisconsin-Madison. We'll talk about estimating non-parametric time series network models.
Thanks very much, Lisa. Thanks very much to the organizers for putting on this great workshop and great program. And thanks very much to for the invitation to speak here. And so this is based on joint work with a PhD student at UW-Madison, Henry Howgill. So I'm going to talk about estimating sort of time series network models, and so in particular talking a little bit of detail about some of the applications, but broadly the kind of data that we're observing here is multi-variate time series. So you can imagine that this sort of arises in a number of applications. So for example, in neuroscience, you could think about sort of multi-variate spike trains. So we observe sort of multiple sort of neurons firing within a brain. You could think about observing some sort of climate variable at different locations. From a social network point of view, you could think about people posting at different points in time, financial time series, and there are many, many other applications where you observe multivariate time series. And so kind of the broad sort of scientific question that we're interested in is, how do we, how do different sort of series or actors within that within that network sort of influence each other? And so can we kind of run an influence network based on these multivariate time series? So Lisa's just given a very nice talk about networks, and just to be clear, like the notion of network here is totally different. So in the context of Lisa's work, she's talking about networks as being data. Here, like networks are kind of parameters to be estimated from this multivariate time series. Okay, so to go into a little bit more detail about sort of the applications that motivated this work. So in the context of computational neuroscience, sort of one fundamental question that they're interested in is sort of how do different neurons influence each other in the brain, or in particular this sort of notion of functional connectivity. So you can imagine sort of probing different regions and then observing maybe sort of spike train data over time. And then your question is if one particular voxel fires, does that trigger or inhibit firing events in other voxels? And so that's sort of can we learn some sort of influence network from that? So another application that I've just started to work on, and it's become kind of very topical in the last 12 to 18 months, in particular in kind of political science or social science or in social networks, is this notion of how does sort of information or disinformation or misinformation or anything else spread within a social network. So you can imagine that someone posts on Facebook or tweets or sends some kind of information, and that might trigger events from other people. And so the question that you're interested in is who influences whom within a social network. So these two applications both involve kind of event data. So you're kind of just saying, does a discrete event occur at a particular point in time? But what I'm going to talk about today can also be applied to when you have continuous values for the time series. So in particular, one sort of application that naturally arises a lot is in financial time series. So you might look at sort of stock returns or stock prices and how they evolve over time. So if one particular stock price increase, does that sort of trigger other stock prices increasing or decreasing? So once again, you're trying to you're trying to estimate some sort of influence network parameter from that. So broadly, the goal of kind of what we're trying to do here is that if you kind of observe sort of data that's like this, so in this case it's event data. So here you have like five series, and you might you observe sort of the events occurring over time like this. And so the question is, if you're given this kind of data, and this is sort of generated maybe according to some model, and I'll sort of talk about what these models are shortly. Your goal is to kind of learn this underlying network or some underlying parameter matrix. So these numbers sort of are some measure of sort of the strength of the influence of one node on another. And so your goal is to kind of estimate this from the multivariate time series data that you observe here. So that's kind of an introduction to the overall problem that I'll be looking at, and so I'll sort of go into the model and some of the guarantees that associated with that. So I'll sort of start by talking about some of the main challenges and the prior work associated with this problem. Then I'll, in the title of the talk, I sort of talk about non-parametric approaches. So I'll start with talking about the GLM network model and the parametric approach that we use, because I think it's sort of easier to understand the parametric approach before moving to the non-parametric approach. And then I'll talk about the sort of sparse additive network models that that we'll be using here. So that's where I'll sort of kind of define the model we'll be using here. Then go into the estimator, the estimating procedure, and a little bit into the algorithm. And then I'll start to talk about the theoretical guarantee. So that'll really be the main focus, is developing some sort of sample complexity or rate guarantees for the particular models that I'm talking about. And then I'll briefly talk about the proof, and then go into some empirical results, both for simulations and then real data. And then I'll wrap up. Okay, so remember that the goal was to sort of use multivariate time series to estimate some influence network. There are a number of challenges associated with this, and probably the most challenging and the most difficult to answer, and one that I sort of won't go into in too much detail, are like what are actually suitable network models. So this is very application specific. I'll talk a little bit about a few that we've tried to sort of work with today. And another big challenge is the number of nodes or locations or actors is typically very large in these applications. So in the context of neuroscience, or probing different regions of the brain, you could imagine that you have hundreds or thousands or even millions of regions or voxels that you're looking at. In the context of social networks, once again, you could have thousands or millions or even more different users. And so you're kind of in this sort of high-dimensional setting, which is what makes this problem kind of challenging. And then, in addition to that, we're talking about there's a lot of dependence here. There's dependence across different sort of time series or variables, and then dependence across time as well. So characterizing this dependence is sort of technically quite challenging, and I'll talk a little bit about some of the challenges associated with that. So these are some of the challenges associated with this sort of overall problem. So there's been some related work, especially in the last sort of 5 or 10 years on this particular problem. So I mean, really, this is very related to those of you familiar with just parameter estimation for bar models, or Granger causality. So in the case of parametric linear models, so you can imagine that you have sort of a Gaussian linear auto-regressive process. There's some really nice work by firstly by probably Samantha Basu and George Michaelides, and then sort of some follow-up work. And this sort of is very nice theory, but as I mentioned, a number of the applications that I talk about sort of deal with event data or count data, and so the sort of linear Gaussian assumptions are not so amenable. And as we'll sort of see later, once we start moving to non-Gaussian data, technically the problems become substantially more challenging. There's also been some work on Hawk's process models. So Hawk's processes are kind of a version of measure, like if you want to sort of measure event data, Hawk's processes are a good model for this, and they're continuous time models. The analysis for this is quite challenging, and there's some sort of work in this space, but it's sort of quite hard to interpret these results, especially in high dimensions. We've done a little bit of work in terms of parametric GLM models. So the GLM frameworks are very natural if you want to kind of consider multiple different data types. But we'll see that there are sort of limitations of that. And there's also a number of application-driven studies that use these results, but there's sort of there's not much in terms of theoretical guarantees. And so in particular in this talk, I'm going to focus on a non-parametric approach. So this is in particular to model nonlinear effects, because linear models sort of are somewhat limited, especially in a number of these applications, sort of in neuroscience and others. You sort of expect there to be some kind of nonlinearities, and so capturing that is easier once you start to look at non-parametric models. Okay, so now I'll start to talk about some of the models that we've used, and as I mentioned, I'm going to sort of start with parametric models, because that's sort of an easier place to start, I think, than non-parametric models, and I can also sort of show you what our sort of overall goal is. some particular, to model different data types, we can think about, GLM, auto-regressive models. So here you imagine you observe some xt at different time points. This is an m-variate vector. So m is the number of different series that you observe. And then a to t is this natural parameter belonging to some natural parameter exponential family. So this is kind of what makes this a GLM type model. U is some background mean, and then we have this sort of A star, which is an m by m matrix, which we're trying to kind of estimate from data. And we can certainly think about generalizations of this to higher order models, but as we'll see, even in the case where you have sort of an order 1 model, this is kind of quite challenging. And so basically what our goal is that if we go back to the case that I sort of talked about earlier, here you have m equals 5, and your goal is to estimate this matrix A star given the data. And the question is, how should we estimate A star? But more specifically, like, we're interested in how much data do we actually need to estimate A star. So in a lot of these applications, you kind of have a limited amount of data, and so you need some sort of nice guarantees about how much data you actually need if you want to come up with some reliable estimators of A star. And these will also be influenced by the sort of the parameters that you're actually trying to estimate. Okay, so the parametric approach that we consider is probably the most natural and simple and naive thing that you could imagine doing. So we basically just use sort of maximum likelihood to do that. So if you look at minimizing the negative log likelihood, as I mentioned, you're in the high dimensional setting, so you need some sort of additional low dimensional structure and to sort of incorporate that in some way. So the way that we do that is the way that that's kind of always done in high dimensional statistics, which is to use some notion of regularization. And so here we talk about just a sort of a decomposable regularizer. And so this is kind of the last slide on sort of prior work on parametric models. So in particular, you can think about notions of sparsity or low rankness. And these are sort of very natural if we think about this interpretation of A star as a network, because sparsity sort of means that the number of edges in the network is relatively small. And sort of low rankness, as has been sort of talked about in other talks, can kind of be related to community structure within a network. So in particular, what we showed in prior work, and there's a lot of sort of additional sort of assumptions and characterizations, then a lot more sort of detail to go into, but just sort of in summary, we were able to provide some theoretical guarantees for how much data. So T is kind of the number of time points that you'd want to that you observe. How does the mean squared error scale with kind of these sparsity or layering parameters, the number of series, and like m and then t. And so what's kind of in brackets next to it is what sort of the mean squared error you'd expect to get if you were just to kind of solve do parameter estimation for a regression problem. And the reason why I put that there is because there are actually sort of no sort of lower bounds in this talk, where I'm only just going to focus on kind of upper bounds on the mean squared error. And so, what do you sort of compare to as being good is kind of a natural question. And so what we do for that is to just sort of compare it to what you kind of get in the idealized sort of independent design regression case. So what we can see is that up to sort of log factors, we don't really sort of worry too much about tracking the log factors, and we're sure that these log factors can be improved. But what we can actually show is that you kind of achieve the mean squared error guarantees that you would for the sort of standard regression type problems with independent design. And so this is kind of what we showed, and that's exactly what we're going to try to do in the non-parametric case as well. Okay, so that was sort of everything about what our prior work that we focused on sort of parametric models. And so now sort of the main focus of what I'm going to talk about today, which is really about sort of a non-parametric approach. So as I mentioned, parametric approaches are limited because they only really capture kind of linear effects. But as I mentioned, in a number of the applications, and we'll see right at the end with some data, that there's potentially some nonlinear effects that that are there and that you also want to capture. So just sort of a quick couple of slides about non-parametric models. So here we're talking about M time series where M is large. And it's also sort of widely known that non-parametric models suffer very, very severely from the curse of dimensionality. So for example, if you take like an m-dimensional functions of, say, twice differentiable function, the space of twice differentiable functions, if you're just trying to do sort of simple regression in that case, then the mean squared error scales really badly where sort of m is in the denominator. So you certainly don't have enough data to do this. And so in particular, additional structure is definitely required in this particular case. And so something that Ryan spoke about yesterday, and sort of one sort of thing that people often do to alleviate this curse of dimensionality is to assume an additive structure. So rather than assuming that you're sort of just taking a function of m variables, you can just assume that this can be viewed as an additive model of m sort of univariate functions. And so that's what we do here. And in addition to that, we can kind of further assume sparsity to say that only a few of the variables influence other variables. And there's been sort of a lot of nice work on this notion of sparse additive models. So Pradeep Ravikumar and others developed sort of a nice approach to that. And then Peter Bjorman and Sarah Vandergeer also sort of looked at an approach for that. And so that sort of allows you to do non-parametric regression or estimation even in the high-dimensional case. And so we'll sort of see how that is potentially useful in our context. So this is sort of leads to the model that we'll be studying today. So in the parametric case, the model basically looks like this, where a star jk are these parameters that sort of measure influence between two nodes. So how much influence does node j have on node k? And so this can very easily be sort of replaced by just some function. So rather than just saying that you look at a single, just a linear model, you can just take some function. And this is also very sort of natural in the context of networks, because we can just say that, if we talk about sparse additive models, that if that function is 0, that just implies that there's no edge between j and k. Okay, so the model basically just consists of just doing, effectively doing just regression, sort of m different sort of sparse additive model type problems for this case. Okay, so even when we make this non-parametric assumption, we're talking we need we've reduced the problem to sort of m univariate functions. We still have this issue that we need to make some assumptions about the functions, and so this notion of smoothness through reproducing kernel Hilbert spaces is sort of a very sort of natural thing to do. Reproducing kernel Hilbert spaces kind of include a number of sort of natural sort of function classes, so like polynomials, Gaussian splines, and so on. And I guess the sort of the most important thing to take out of it is that reproducing kernel Hilbert spaces are characterized by eigenvalues and eigenfunctions, and you can express every function as kind of an infinite combination of these eigenfunctions. And there's sort of two norms that you can associate with any univariate function, and they'll sort of both come up in what I'll talk about shortly. There's this sort of Hilbert norm, which is a measure of smoothness of a function. These are inner products, and then there's also kind of the standard L2P or L2Q norm. Okay, and so the estimator that we consider is sort of an estimator that is straight. Once again, we do sort of a penalized likelihood approach. But the penalty kind of comes straight from approaches that have been used for the non-parametric regression models that I talked about. So what we have here is we have two penalties, a smoothness penalty and a sparsity penalty. These are why sort of I introduced both of those norms, because essentially they both kind of come up. These are sort of group L1, L2, and L1 L Hilbert's norm. So the first one's an empirical version of that L2 norm, and the reason we do that is to make it sort of kernelizable and computable. But what this sort of reduces to is kind of it reduces to a convex sort of second-order Cohen program. So in principle, it's computable. It's not exactly that easy to compute, and there are other methods. For example, in the work that Pradeep did or the work that Peter and Sarah did, they come up with methods that are actually sort of easier to compute than this. But because remember that the main focus was on theoretical guarantees, we'll see that there's an advantage in sort of using this particular approach, and it is computable at least. Okay, so I'll remember that in the case of parametric models, like what we sort of used is in some sense a gold standard of what you can expect, because we don't really know how to prove lower bounds. Is what happens if you're kind of talking about just doing parameter estimation for regression with independent covariates. So I'm just going to quickly sort of spend a slide just reviewing that for sparse additive models. So I'm just sort of going through this very quickly, but in some sense, like the problem of sparse additive models, if we're looking at kind of mean squared error or sample complexity guarantees, sort of the story is very simple at a high level in that it really reduces to two sub-problems. One is that you have to figure out which of your S functions are non-zero. And then once you've figured out which of those functions are non-zero, you have to estimate those S functions. So the mean squared error in some sense scales as a combination of two terms, like this S log m over n is the cost of estimating which of these S functions is non-zero. And then this S epsilon n squared, I'll talk a bit more about that epsilon n squared shortly, is just the cost of estimating these S univariate functions. So this epsilon n squared is really just the rate or the cost of estimating a single univariate function. If you can imagine that that a univariate function belongs to a subleved space or a polynomial, it's the cost of estimating that. And so, for example, if you have a polynomial of degree r, that sort of reduces to r plus 1 over n because you have r plus 1 parameters. If you have sort of subleved kernels with new degrees of smoothness or differentiability, this is the rate that the rate that you get. And so these are the results that you get for estimating mean squared error, and we've shown that these are kind of minimax optimal in a number of settings. So the reason I sort of showed this is because this is sort of what we're going to compare the sample complexity guarantees that we derive to for this particular problem. Okay, so now returning to I remember our original sort of model was this. So this is sort of the model that we're studying, and then this is the estimating procedure that we're considering. So now we're moving on to sort of theoretical guarantees, which is sort of the main sort of point of the talk. So we need a number of additional assumptions because, as I mentioned, dealing with dependence is extremely challenging, and so in some sense, an assumption that we make that's probably the most critical to this, and it's not an assumption that we really wanted to make, but because from a practical point of view, I think this is a very strong assumption, and it's also very difficult to kind of estimate or quantify. But this is a very standard notion in probability and statistics of beta mixing or mixing of Markov chains. So you can think of this process as an m-variate Markov chain. And then you can kind of characterize sort of how dependent that is through this beta mixing parameter beta of L or R beta. So in particular, this beta of L is just looking at how dependent random variables are if you look at L steps into the future. And this R beta is kind of characterizing how quickly that decays. So in particular, I mean, the main thing to remember here is that kind of as R beta goes to infinity, you're close to independent. But if R beta is kind of 1, you're about as dependent as you can be. And so remember that, again, this is, I think, very strong, because here you're talking about the mixing of an m-variate process. So, and another big challenge of this from a practical point of view is estimating this. I sort of don't know how to do. So this is really sort of useful from a theoretical point of view. And so, I mean, one of the reasons we do this, so there's a couple of reasons why I think this is useful to do. I guess the first one is that we really didn't know how to proceed without doing this. So maybe there are other ways to impose some kind of mixing, but sort of we aren't sort of sure how to do that. And I guess the second thing, and what we'll see shortly with the question. So yeah, and so another thing that we'll see is that at least from a theoretical point of view, this R beta quantity, which sort of quantifies how dependent this process is, we can sort of see how that impacts the mean squared error and the overall rates question.
Yeah. So I mean, this is perhaps a bit unfair, but it seems to me that assuming mixing is almost the wrong way to go. Like, consider a model where literally there's no noise,
Yeah.
and your sequence is perfectly predicted by functions of the previous variables. That should be very easy to estimate, right? But in that case, your beta constants.
So what do you mean by no noise, I guess? Like you
Like
just...
xt plus 1 is a function of xt.
Right.
I should be able to estimate in that
Right.
setting much
Right.
more easily than in the case where xt plus 1 is like a function of xt plus a boatload of noise.
Right.
Right? But
Yeah.
in the latter case, I'm probably very close to independent, so my beta mixing coefficients are near 0.
Right.
Whereas in the former case, my beta mixing coefficients are 1.
Right. Right.
But it's that case that's, at least to my intuition,
Yeah.
that's the case I should actually be able to solve easily.
Right. So I guess, yeah, I mean, that's a good question. Like, I don't know how this works in the deterministic case, really. Like,
But yeah, I mean, so those are some limits.
Yeah.
But like somehow,
I mean, I guess, like, we really did not want to impose this. We just couldn't think of a better notion of, like, characterizing the dependence. Like, I don't know. Like in the parametric case, you can kind of impose assumptions on the parameters to make that happen, but we weren't really sure. So
but I guess even in the parametric case, like, it seems like the problem gets easier the farther you are from mixing.
Yeah. So this is a good
linear model, like xt plus 1 equals axt
Yeah.
plus noise.
Yeah.
Like that process mixes when a is
Yeah.
0,
Yeah.
but when a is 1, it's
Yeah.
super easy to estimate.
Yeah. So this is an interesting point. There's this sort of sorry.
I guess the issue there might be that you essentially don't have more samples in that case. So even though there is this functional
No, I agree with
relationship-
you on this, but this is not exogenous noise. So if the noise were exogenous, that would be one thing, but this noise is endogenous to the process. So when you have endogenous noise, the farther you are from mixing, that means you're actually getting experiments with a huge amount of power. I mean, basically your SNR here should be going to 1 as the beta mixing coefficient. Or sorry, your SNR should be going to infinity as the beta mixing coefficients go to 1.
Yeah. No. This is.
Maybe this should be offline.
No, I mean, this is like
It's gonna be-
this is a really good point because I mean, this is like there's this sort of trade-off between sort of the Markov chain mixing and estimation because
But
estimation is
I argue
easier
there
because
shouldn't be a trade-off in the case in the noise model.
but then like your XTs could kind of blow up, right? And then,
Yeah, for sure.
yeah. So I mean,
I mean, but like think about just the one-dimensional case. Xt plus 1 is axt plus
right.
Gaussian noise.
Yeah.
When a is bigger than 1, I actually get exponentially fast convergence to the true a
Right.
by
Yeah.
estimating, and that's, I mean, in that case, I'm not mixing at all.
Right.
Yeah, so what? So who cares if your xt blow up?
At some point you start receiving samples.
Right. Yeah.
Says who?
The process diverges.
That doesn't matter.
Or I guess we'll.
Do we have to? I mean, there was. Why do
You're
I?
not covering
All right.
I mean, the time series is kind of split up whether you're modeling the mean or the covariance, and whether you have an integrated process like what you're talking about, or a stationary process. And it's fine if you stick in a framework. So you just pick the framework. We're fine to stick with it, right?
I think I have to reel this enough.
Right.
Maybe we should.
That's all right. But it's a good point though. But yeah. I guess we'll-
What?
All right. All right. Okay, so so one of the main goals was to get some sort of mean squared error or theoretical guarantees for doing this, and so as I mentioned, this sort of R beta quantity sort of emerges in terms of the the rate. So what sort of an important parameter here is m, which is which is related to R beta through this quantity. So what you can see is that as R beta goes to infinity, sort of m is just order of t, and for R beta, so close to 1, like you kind of have m being close to a constant. And so what we can kind of see here is that as R beta goes to infinity and m is order of t, we kind of get the same rates up to log factor as we do in the kind of independent case. But as as R beta goes to 1, we kind of get this sort of suboptimal scaling of, well, I mean, not necessarily suboptimal, but this sort of these sort of weaker results in terms of the sort of prediction error rate. And so this is sort of how R beta sort of determines how that influences the rates of convergence, because m is in some sense how much data you're actually getting when you kind of block the time series. And so if we wanted to compare that to the independent case, I've sort of just said this, but you know, we can see that if m is order of t, which means r beta goes to infinity, that's sort of like having a lot of blocks or a lot of independent data, and we get similar rates. But then as m sort of gets close to 1, we get weaker results, which is kind of what we'd expect. And I guess the proof sort of follows it follows some standard steps from empirical risk minimalization. So in particular, initial steps are kind of similar to the independent case, but then we're kind of dealing with dependent data, and so we sort of use this classical or this blocking technique, which is where m is kind of the number of blocks, and that's why that kind of shows up in the rate. And so we kind of deal with that, and then we use empirical process and concentration type bounds for beta mixing processes. So in the independent case, we just used empirical process and concentration bounds for independent random variables, but here we're dealing with general processes.
You need to know this data in order to do this blocking, or
well, this is a technical. This is from a theory point of view.
I'm
so
sure it's actually not something that.
yeah. So this is like one of the things like estimating this beta is really hard, and that's sort of an open question. But so the blocking is for theory. It's not something that's sort of easy to do in practice, as far as I know. Okay, and so one other thing, I guess, about this, and this is also sort of related to the techniques, is that I sort of presented mean squared error guarantees in terms of prediction error. But a natural question you might consider is, what if you're interested in the population norm or error? And we can get results in that, but what's kind of interesting is that there's a bit of a difference between them. And so in particular, in the case where you're pretty independent, which means m is like order of t, these results actually sort of match the population and empirical error. But then what you'll see is that as you become more and more dependent, the errors you get in terms of population norm are actually sort of they're slower than what you get in prediction, which again sort of makes intuitive sense if you sort of think back to the lasso applied to linear regression. When you have independence, you get the same rates for prediction error and estimation error. But then if you have dependence, you can sort of still prove something about prediction, but you can't really prove much about parameter estimation. So that's sort of, this is the second way that this R beta is sort of capturing the effect on the mean squared error. So then from a computational, now sort of move on to the simulation and kind of real data type results. And so I mentioned that this is implementable, but it's actually pretty hard to implement, and we haven't I actually don't know of a good implementation of this optimization problem. I mean, we tried it in CVX, but that's very slow, so we didn't really use that for the experiments. And so what we ended up using was this sparse additive models, or SAM package in R. But this is a simpler, a different optimization problem where you just set the sort of smoothness penalty term to 0, or the smoothness regularization parameter to 0. We used polynomial kernels to sort of keep things simple, and then looked at different values of n and t here, and we can because we're dealing with simulations, we can kind of choose lambda t either by cross validation or in a theoretically optimal way. And so this is, just a simple simulation to just sort of see that we sort of roughly see that the mean squared error scales roughly is 1 over t to the something. Sort of what that something is hard to sort of really say, because it depends on these mixing coefficients, and we sort of set the Markov chain so that we know that it mixes, but we don't really know what that mixing coefficient is. Okay, so now it's sort of moving on to the real data, sort of applying this to real data just to sort of do a sanity check to make sure they're at least doing something that's sort of not crazy. So it's often difficult or impossible to actually validate these models. It's very easy to generate these sort of networks, but difficult to validate. So there's a couple of things that we can do and that we'll do. We can either use some sort of data visualization to sort of look at these networks in some ways, and then maybe if we have some outside domain knowledge, say something about that. or another sort of natural way to do this is through out-of-sample prediction. And so we're going to do that in the context of Chicago crime data set that I'll talk about. So in particular, I mean, crime in Chicago is sort of something that, particularly in certain areas is, something that sort of is sort of known to sort of happen a fair bit. And so in particular here we have Chicago's kind of divided into 77 regions or community areas, and this is sort of a map of Chicago and how it's divided up. And so the question that we're looking at is, do sort of crime events in one region trigger or inhibit crime events in other regions? Okay, so the first thing that we did is we just sort of tried this for a number of different communities and in terms of just prediction errors. So because we're dealing with count data rather than using the mean squared prediction error, we use this kind of Pearson statistic loss. And so what we can, I mean, the main point of this is just to show that there seems to be some benefit in going from like R equals 1, which is the parametric type of model, to sort of higher order polynomials. So it seems like there's some sort of nonlinear or non-parametric structure that we're capturing because the loss is sort of lower for a higher degree, and that's sort of true across other community regions too. And then in terms of the other validation that we can consider is visualization. And so what we do is we can kind of treat this, like we can sort of treat this M by M matrix in some sense as like a 0-1 matrix as well, and then do some sort of clustering to see if the clusters make some sense. And this is not, I have no idea about what the ground truth is, but what you might expect is that, there's some sort of notion of, that there's sort of spatial effects. So if regions are close together, you might expect some sort of, spatial dependence. And we can kind of see that, and I'd sort of argue, although it's sort of very tenuous, that maybe if you look at higher order polynomials, the clusters look a little bit cleaner. But again, that's sort of kind of speculative. And here's another plot. If you actually and Lee's also talked about potentially having covariate information. So if you actually use the spatial covariates, you, as expected, would expect things to look a lot more spatially co-located. And so we do that here for both kind of the parametric case and then the sort of the degree 2 polynomial case, or the degree 3 polynomial. Sorry. And again, I'd sort of argue that, again, it's sort of debatable, but the clusters look a little bit cleaner for the higher order polynomial. And so this is just sort of just a bit of a sanity check that what we're doing seems at least somewhat sort of not totally crazy. Okay, so in terms of sort of conclusions and future directions, so we want to kind of we've developed this sort of non-parametric, or applied this non-parametric framework for estimating these sort of influence networks using multivariate time series, and provided some sort of sample complexity guarantees in terms of these mixing coefficients. In terms of future directions, these models are sort of not overly realistic, so we'd like to sort of think about maybe more realistic models. Also sort of related to sort of what John asked about, I mean, to me there's this notion of sort of mixing and also estimation, and I don't know, it's sort of like, I think it's pointed out by John, like in some sense, like the way I sort of see it is that the more the Markov chain mixes, the harder it is to estimate because there's less dependence. And so I don't know sort of how this trade-off, or maybe it's not a trade-off, really gets characterized. And then related to the question that Rob asked, actually estimating these mixing coefficients or using alternative assumptions would be nice. As far as I'm aware, there is some work on estimating mixing coefficients when you have like univariate or a small number of time series, but how this extends to when you have a large number of time series, I'm not sort of sure. There's no sort of lower bounds on this, and I don't really know sort of how to prove any lower bounds, but that's sort of a natural kind of question to see if this is optimal in any sense. From a practical point of view, I mean, in a lot of these settings, there'll be sort of periods of time where you may not observe data, or more importantly, even hidden variables. So if you think about neuroscience, there's a number of neurons that might be sort of mediating behavior that you don't observe, and actually incorporating that into the model would be nice. And also, as I mentioned, there's sort of this issue of scalability of the algorithms. So there are sort of a number of sort of open questions associated with this. All right. Thanks very much.
So for the last point, you may want to look at the multiple kernel learning,
Right.
which is very similar,
Yeah.
for which is a
Sure.
sequence of algorithms
Yeah.
for large scale problems.
Right. Okay. Okay.
So in the, if I'm not mistaken, in the bounds you're referring to in the non-parametric regression case,
Mm.
not the auto-regressive case that,
Yeah.
that you had worked on with
Right.
your co-authors.
Mm.
In that case, the features were like either uncorrelated or had weak correlation.
Yeah, we treated them as independent. Yeah.
So I missed it, but what was the assumption on the different dimensions of the vector autoregressive process here?
Well, so like I guess they appear in the rates, like through like m is the dimension here. So like big M, sorry, is the dimension here.
I
so-
meant what's the assumption about is there some dependence between those dimensions of the process?
So we just like I guess the dependence is characterized through the mixing. So that's why it's not satisfying because it's all sort of hidden in the mixing assumption
Right.
basically.
So I guess one maybe thing that may not be as pessimistic as you're expecting is that I think if there was substantial correlation from the features, then you would not get the rates that you had written even in the kind of non-parametric.
That's true. Yeah, that's right. Yeah.
So you shouldn't be expecting those.
No, I agree. Yeah.
Like what's the mixing?
Yeah, and so that's sort of like, can we prove some like lower bounds in that case that might be useful? Yeah, because as you say, you wouldn't expect fast rates, and if you didn't make assumptions on the covariates. Yeah. Yep.
On the second last point in your conclusions, the hidden variables. I mean, something in your example, it could be right that you have events that you actually don't observe and that trigger sort of several events with a different sort of time lag, and then it just looks like you're getting an additional edge there, right? So have you looked at? I mean, in principle, one could also look at invariance over time. So you could actually, if you look at these functions, how they evolve over time, this could be actually a good hint for whether they are hidden variables or not.
Right. That's a good point.
And maybe a related question. I mean, sorry if I missed it, but do you get confidence intervals for these effects?
Not at this stage. Like that's something that we're like working on.
Very useful to see whether there's a significance.
Yeah, exactly. Yeah, so that would be useful to do, and we don't have them at this point. Yeah.
Any more questions?